This paper presents AutoAI TS, which is AutoAI for time series forecasting. This is work from IBM research. Constructing and tuning pipelines for forecasting more for forecasting problems on a given data set is challenging because we have a wide variety of models available. There are various classes of models for forecasting, and more recently there has been a wide variety of transforms that can be applied to the data before we can train the models. So figuring out the best combination of transformers and estimators, as well as the best parameters, is compute intensive and also time consuming. And it also needs a lot of expertise, both in the domain as well as the technical expertise in the given models. Automated machine learning techniques have been proposed in the past in the literature, but most of them focus on classification tasks and IID data sets. The ones that focus on time series modeling are mainly focusing on specific models. More often, it's classical statistical models. For example, automating a VIMA or automatically finding best coefficients and parameters for exponential smoothing or state space systems and methodologies. And the other challenge is that once you find the best model, the same best model might not work for all sorts of data sets. So if the domain that the data comes from changes, we might have to rerun the whole search again. The goal in this presentation and this paper is to propose a zero-conf system that can build search and tune pipeline for the given data without asking user for any specific configurations. And of course, the user can specify configuration if the user knows more about the domain or the system, and they want to build pipeline in a specific fashion. They can do so. The goal here is to automate the AI model selection by transparently combining various classes of time series models into an extensible unified system called AutoAI TS. And the AutoAI TS needs to be extensible because we want to include and incorporate the latest proposed models to the system and be able to search those as well for a given data set and to see how they perform for the given user data. The AutoAI TS creates pipelines from transformers and estimators and automatically ranks them to find out what's the best pipeline. It's important to note that we don't assume any prior knowledge of the input data, so the user just have to drop their data set to the system, and the system does the rest of the job. TDOB, which is a proposed pipeline ranking mechanism, is used to rank the pipelines in order to find the best performing pipeline for the given user data. The system supports a variety of forecasting models that include statistical models, machine learning models, the mix of statistical and machine learning models, as well as deep learning models. We have a variety of transforms that are combined with the forecasting model in order to create pipelines and then search through those pipelines. As I mentioned before, we create pipelines, and those pipelines are basically sklearn style pipelines. They implement all the pipelines in our system implement common APIs. Those APIs follow a scikit-learn style in which the estimators implement fit and predict, as well as core methods, whereas the transformers implement fit and transforms depending upon if they're stateful transformer or stateless transformers. they might, if they are stateless, they might just implement transform method only. Our TDOP mechanism, which is a pipeline selection mechanism, is also implemented as an estimator, which invokes the corresponding methods of the candidate pipelines, as we will see later in the presentation. To ensure the compatibility of our transforms of various sets of transforms and estimators, and to be able to integrate them into pipelines, we ensure that all the pipelines adhere to the same semantics, data semantics, and the same input-output schema for the data. There are various pipelines in the system. In the statistical pipelines, we have RIMA, whole winters, additive, and multiplicative versions. We also have BATS model, which is Box-Cox transformation, ARMA residuals, trend, and seasonality. The whole winters implemented in this system are single seasonal models, whereas the BATS is multi-seasonality state space models that can capture complex seasonalities. The ML models are also implemented in our system. There are various ML models such as ensemblers, random forests, SVM-based models. There are some hybrid models which combine both the trend which combine both the statistical and ML pipelines. All those pipelines support various use cases, for example, univariate, multivariate, as well as single and multi-step ahead. The overall system is sort of a component-based system in which once the data is ingested by the system, it goes through quality check. The initial quality check is to ensure that we know about the properties of the data, if there are any negative values, if there are any missing values that needs to be interpolated. And then once we have data in a good shape, then we build a zero model. The zero model is basically providing first the user a model that they can immediately use. Also, the zero model provides baseline performance of the system, and the aim for the rest of the pipelines is to perform better than the baseline. Once the baseline model is trained, we run through a component that's called lookback window computation, which automatically computes lookback window from the given data set. But different ML and deep learning pipelines, they use history of values, which we call lookback window, in order to train and forecast, train models and forecast values. And that lookback window is most of the time dependent on what is the actual data, and also sometimes what models we are using. So we have a mechanism that automatically finds the lookback window length. Once we discover the optimal lookback window for the given data set, then the pipeline generation starts. The pipeline generation basically combines the transformers and the transformers and the estimators into a pipeline, and these pipelines are a diverse set of pipelines and heterogeneous pipelines. Some of them are statisticals, as I shown before, statistical ML mix and ML models. Once the pipelines are constructed, they are passed down, they are called by or invoked by our TDOP mechanism, which is the pipeline ranking mechanism, which basically tries to evaluate those pipelines and rank them based on their projected performance. Once the best pipeline is chosen, that pipeline is actually returned to the user that pipeline is first trained on the whole data set and then returned to the user. So we can see in the figure, the green part of the data right here is the holdout set from the given input data that we use to evaluate the performance of each pipeline in the TDOP run. All the performance that we measure and that we measure for ranking the pipelines is measured on the holdout set. And once the best pipeline is selected, the whole data set, including the holdout data set that we've separated from the given input training data, is used to train the final best model. Automatic look-back computation mechanism is, as I mentioned before, tries to figure out the best history window, or what we call a look-back window, in order to train the system, to train the ML models, and to forecast the future values. This look-back window length is somewhat dependent upon the data itself and what's in the data. So that this needs to be dynamically computed every time we have new data sets to run on. The proposed model, the proposed mechanism for the look-back computation is based on two types of analysis. We do timestamp-based analysis as well as the value-based analysis. And then we do post-processing, in which we combine the timestamp-based analysis and value-based analysis in order to basically create a sorted list of the look-back windows. In this sorted list of look-back windows, we eliminate all those look-back windows which don't satisfy certain sanity checks, and for now we return the best or the highest weighted look-back window, and that length is used in initialization or construction of the ML pipelines, or all the pipelines that need the look-back window length. TDOP is our pipeline selection process. This is based on a previous published paper that's called DOB. This is the time series version of that DOB algorithm. The way this TDOP mechanism works is that it allocates smaller subsets of the data to each pipeline and progressively increases the length of the training data set. As we can see in the figure, that the test data is fixed. So once we get the data, we split it into the test, which is our holdout set in the previous chart, and the train. In the test data is not provided to any of the pipeline during the TDOP pipeline ranking mechanism. The training data is allocated to those pipelines, and incrementally, this is increased incrementally from, as we see, from top to bottom. First, we allocate small subset of the data and train the pipelines on those, and then we rank the performance based on the test data set. The best performing pipelines are stored in a priority queue, and those pipelines which perform best, they get more and more data. And the pipelines that perform worse, they will drop out of the evaluation mechanism, and thus only the best pipelines or the best performing pipelines will get progressively more and more data. The more details can be found in the paper on this, how we allocate the data incrementally and change the allocations dynamically as we go on in our TDOP iterations. The more important, the important thing here that pertains to the time series is that we start allocating the data in the reverse fashion. So we allocate the latest data, small subset of the latest data first, and then we increase from sort of right to left by increasing the the training data so that our models are always trained on the latest chunk of the data. Once the best pipeline is selected, we train the model on the whole data set. That will include the test as well, because the test was initially part of the data that was given by the user for the training. So we make sure that the best pipeline is trained on the whole data set that was provided by the user. Next, we have an extensive set of benchmarks. We developed a benchmark an evaluation platform that's based on containers. We tested our system um, against state-of-the-art frameworks that were available to us. We tested and evaluated various cases on sort of univariate data set, multivariate data set, and we also tested for one step ahead and multi-step ahead forecasting. The SOTA frameworks that we tested our system against was PMD ARIMA, DPAR, Window Regressor, PyAF, Rolling Regressor, Beats, Motive, Component, and Facebook Profit. Please note that we provided the same amount of data in the same sort of platform to both AutoAI time series as well as the SOTA. So the benchmark framework that we used for evaluation performance measurement did not differentiate between the SOTA as well and the AutoAI time series. For the benchmarking framework, all the SOTA state of the art as well as AutoAI time series, they were the same kind of system to evaluate. And we evaluated all of them on the same test train splits. More details about the data sets itself can be found in the paper. We also tested our system specifically on synthetic data set. The goal here was to figure out that our system or the models that we implemented in our AutoAI time series system can detect various signals various known signals, and also it's resilient to the noise. Just like in case of figure B, we introduced spikes, and in the case of C, we have sort of a very noisy kind of data, but we wanted to see if our system is able to detect that. In the D case figure, we have season that changes and gets flat, and then the season starts again. So that's as we can see that the orange line, which is the predicted values, they are nicely following the actual values or the true values, which means our system is able to detect or predict the trends and the seasonality reasonably. Then we tested our system on real world data sets. There's a whole 62 list of 62 data sets across different domains and sizes. We tested our system as well as the state of the art system on them. As far as for the accuracy, we used SMAP measure to measure the accuracy of all the algorithms and models, including AutoAI time series. And we noticed that AutoAI time series on average performs very well. The figure shows the ranking of the pipelines, which is basically how well the pipelines and the algorithms are performing on various data sets. As expected, our AutoAI time series takes slightly longer on the training time, and that's because we are running the TDOP iterations, which are multiple iterations over time. We also did multivariate time series tests up to 10 dimensions for single and multi-step ahead. Details can be found in the paper. All the detailed measurements of the accuracy and times are provided in the paper. In conclusion, we are basically providing a design and implementation of a zero configuration system called AutoAI time series. It transparently integrates various classes of prediction models. In future, we are planning to include even more recent models into the system and try to incorporate various other aspects of time series analysis into our system. Thank you.